Biomass essentially refers to the total mass of living organisms within a specific area or volume, serving as a tangible or measurable sort of guide of the living material present in an ecosystem. One effective way to visualize biomass is through biomass pyramids. These pyramids represent the amount of living matter at each trophic level, starting from producers at the base and moving up to various consumers. Typically, biomass decreases as we move up the trophic levels. This decline reflects the energy loss that occurs at each stage, primarily due to metabolic processes and heat loss, which is that 10% rule, which means there's less energy available to support higher level consumers. Interestingly, in some marine ecosystems, biomass pyramids can appear inverted. So this unusual pattern arises because phytoplankton, the primary producers in these environments, reproduce and turn over so rapidly that their biomass at any given moment is lower than that of the consumers above them. Despite this inversion, energy flow still follows the expected direction from producers to consumers, which is interesting. Overall, biomass provides a direct link to energy stored and productivity within ecosystems, helping us understand how energy is accumulated and transferred across different levels of the food chain. Okay, so now that you understand kind of the 10% rule, the biomass, let's explore the vital roles decomposers play in maintaining energy flow and nutrient cycling, because they act as nature's recyclers, breaking down dead organic matter and returning nutrients to the soil, which is essential for sustaining producers and health of ecosystems. Okay, so decomposers, or detritivores, play a really important role in maintaining the balance of the ecosystem. They recycle matter and sustain nutrient cycles. They're kind of the unsung heroes that ensure energy continues to flow within food webs by breaking down organic material. First, decomposers such as fungi and bacteria specialize in breaking down dead plants and animals. Through this process, they release vital nutrients back into the soil, making them available again for producers like plants. Without this nutrient return, producers would struggle to grow and sustain the ecosystem. Next, detritivores, including earthworms and certain insects, actively consume dead organic matter. Their feeding accelerates decomposition by physically breaking down material, which complements the chemical breakdown by decomposers. This is a collaboration that helps recycle nutrients more efficiently. Together, decomposers and detritivores complete the nutrient loop. By doing so, they prevent the buildup of waste and dead material that could otherwise accumulate and disrupt the ecosystem. Think about if we didn't have people coming and collecting our trash every day. There's going to be an accumulation of trash. Such blockages would hinder nutrient availability and interrupt the energy flow that producers depend on. Finally, the nutrient recycling performed by these organisms directly supports new plant growth. This nourishment at the producer level is essential because it sustains energy transfer up through the food chain, keeping the entire ecosystem functioning smoothly. So building on this understanding of nutrient recycling, let's now look at how energy production varies under different respiration conditions, so aerobic and anaerobic processes, and how these impact the energy flow and cycles within ecosystems. So how organisms generate energy under different environmental conditions and how these processes impact ecosystems is pretty interesting. Aerobic respiration, as the name suggests, requires oxygen. Aerobic, oxygen. It's the most efficient way for organisms to extract energy from nutrients, producing a higher yield of ATP, the energy currency of cells. This efficiency is why most multicellular organisms, including humans, rely heavily on this process to meet their energy demands. In contrast, anaerobic respiration takes place in the absence of oxygen. So absence, because it uses alternative molecules as electron acceptors. It produces significantly less energy. This process is common in environments where oxygen is limited or absent, such as deep soil layers or stagnant water bodies. Some organisms, like yeast, utilize fermentation, a type of anaerobic metabolism. Fermentation allows these organisms to generate energy without oxygen by converting sugars into simpler compounds, which is essential for their survival in oxygen-poor conditions. The ability to respire anaerobically is a crucial survival strategy for many microorganisms. It enables life to persist in diverse habitats where oxygen is scarce or limited, expanding the range of ecosystems and influencing the overall flow of energy within them. Altogether, these respiration pathways not only determine how much energy organisms can produce, but also influence how energy and nutrients circulate through ecosystems. So understanding these mechanisms will help you appreciate the complexity of energy cycles in nature.